Hello and welcome back to the season finale for Calc 2, Taylor and Mclaurin Series. Now these are super cool. These allow us to not only approximate a function, but exactly approximate a function. In other words, represent a function, any function, in polynomial term. And so I guess we should just hop right into some equations so that we know how to evaluate or approximate a function. So what the Taylor series tells us is that f of x equals the sum from n equals 0 to infinity. Notice this is our series notation of the f to the nth prime evaluated at our point A divided by n factorial times x minus a to the n, where a is the point that we want to approximate from. And so basically what this is going to do is, say we had the function e to the x, well first we would get just a point A, and then we would add onto it a linear approximation. We would get this, and then we would get a quadratic approximation. We would get something like that, and then we would get a cubic approximation, something like this. And you'll notice it starts to hug the curve more and more until at infinity, it's just the curve. And I mentioned Taylor and Mclaurin series at the start of this video. A Mclaurin series is just this, but a is 0. So we get the sum from n equals 0 to infinity of f to the nth prime evaluated at 0 over n factorial times x to the n, because a is 0. Pretty simple stuff. It might look intimidating, but it's pretty simple. Let's get really used to these, and let's prove Euler's identity with these Mclaurin series. We could prove it with the Taylor series, but there's no real point of doing it. I guess we could say it's just Taylor series at 0, so let's not leave Taylor out of this. But Euler's identity, it tells us that e to the I pi equals minus 1. And I proved this a few months ago by myself. Well, obviously Euler proved this before. But what we're going to do is we're going to find the Taylor series for e to the x. And what that is going to be is, well, let's take e to the x. This is our 0th prime. Let's prime it again, we get e to the x. Prime it again, we get e to the x. Let's evaluate these all at 0. E to the 0 is just 1. So that means that e to the x equals the sum from n equals 0 to infinity. And we know that our f to the nth prime evaluated at 0 is always just 1. So we can just put a 1 here over n factorial. And we know that's x to the n, so it's just x to the n here. This is pretty easy to write out. This is just x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, on and on until x to the infinity over infinity factorial. So we're going to simplify some of these terms. This is just 1. This is just x. And there is the Mclaurin series for e to the x. Now, let's find the Taylor series for cos x. So that's our 0th prime. Let's derive it with respect to x, we get negative sine x. Let's derive that with respect to x, we get negative cos x. Let's derive that with respect to x, we get sine x. And if we derive sine x once more, we'll be back up here. Let's evaluate these all at 0. What are we going to get? Well, we're going to get cos of x evaluated at 0 is 1. Any sine at 0 is 0. And negative cos x at 1 is just negative 1. So we're going to have a very similar Taylor series for this. We're going to get that cos x is going to equal 1 minus x squared over 2 factorial plus x4 over 4 factorial minus x6 over 6 factorial, on and on and on. Now, let's find the Taylor series for sine of x. Well, we're going to get something very similar. Let's derive sine of x, we get cos of x. Let's derive cos of x, we get negative sine of x. Let's derive negative sine of x, we get negative cos of x. And if we derive that again, we're going to go back up to sine x. This is going to give us the Mclaurin series, or Taylor series centered at 0, of x minus x cubed over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial, on and on and on. Well, let's plug in I into e to the I times x. Well, what we're going to get is e to the ix equals 1. Wherever we see x, we plug in ix. We get ix plus I squared is negative 1, so this is minus x squared over 2. This is going to be minus, let me make sure I get this right. I is root negative 1 cubed. We get negative 1 times I. So we get minus I x to the cubed over 3 factorial. We're going to get plus x5 over 5 factorial. And so what we're going to get is well, let's separate some of these terms. This equals 1 minus x squared over 2 factorial. I think I lost my x to the 4 term. Oh, this isn't supposed to be 5, this is supposed to be a 4. X to the 4 over 4 factorial. And then I think we're going to have a plus I x to the 5 over 5 factorial, I believe. Yes. I haven't done this in a while now. And if we had me sat here thinking about this, we'd be here all day. I think this video is already running pretty late. But what we're going to have is 1, and I'm going to put some brackets around this, 1 minus x squared over 2 factorial plus x4 over 4 factorial minus x6 over 6 factorial plus, well, let's factor the i's out of our other terms with I. We've got I times x minus x cubed over 3 factorial plus x5 over 5 factorial. Let's put dots at the end of this to signify that it continues going, even though we're not technically supposed to do this. Well, let's look at this. cos x. This, sine x. So we've got e to the I x equals cos x plus I sine x. Let's try to get rid of these I terms. Well, sine of pi is 0. So we can say that e to the I x equals cos of pi. Because our sine x goes away, cos of pi is -1. E to the I x equals -1. And this is this proven. Beautiful. That's Taylor and Mclaurin Series for you guys. Thank you so much for watching my Calc 2 series, even if this was the only video that you watched. I really appreciate every single one of you. And I hope to see you in the Calculus 3 video. I'm out of breath from that proof. That is seriously some serious stuff. Thanks for watching.